Okay, thank you very much for the introduction. So I'd like to mention my co-author, Dr. Konstantin Ustinov from the Russian Academy of Sciences. The work we have done is to formulate an elasticity technique to solve one of the still open problems in the mechanics of bimaterial layers. And the problem is the derivation of accurate boundary conditions for beam plate models used to describe the detaching layers. So these conditions differ from condition of perfect clamping, the so-called built-in condition. They are elastic clamping conditions, and they are typically described in the literature by root rotations and root displacement. And you can see here example for a bimaterial layer and for a thin film on a substrate. So the root rotations, for instance, are defined as the relative rotations between the crack tip cross-section, between the detached and the intact part of the specimen. And these root rotation and root displacement account for the near tip deformations. And the near tip deformation can be quite relevant, especially in the novel material system, which are used in nowadays applications. So I'm referring, for instance, to sandwich composite materials used for aeronautical or naval application. And these materials are characterized by an extreme elastic mismatch between the faces and the core, or to materials used in soft electronics applications. And again, we have extreme mismatch of the elastic constant. And also I'm referring to orthotropic materials and crystals, which have extreme orthotropy ratios. Now, in all these cases, the near tip deformation can be large. And the near tip deformation may profoundly affect the behavior, the fracture parameters, and crack growth. And I will show you in the following 3 different examples of problems where these effects are quite relevant. So the first is a case of structure in which we have the presence of shear forces in the layer. Here you see, for instance, a single cantilever beam sandwich specimen, which is a test which is currently being considered to become an ASTM standard for the characterization of D-bond fracture toughness in sandwich composite. And in this specimen, as well as in all DCB specimen, shear and near tip deformation combine so that they have a profound effect on energy release rate and mode mixity ratio. And this is well known in the literature. And for this reason, people have been using approximate model, such as the model of a beam on an elastic foundation, where the spring stiffness K is used in order to account for this near tip deformation, or the model of modified beam theory, where a built-in beam has an increased length, again, in order to account for the increased compliance due to the near tip deformation. Now, if we look at the expression of the energy release rate in this specimen, and the formula on the left is an exact elasticity solution, which is valid for thick core sandwiches, while the formula on the right comes from the approximate model on top. Well, you can see that the effect of shear and near tip deformation is in those terms with the red brackets. And you can see that they depend linearly on the length of the crack. And this is why these effects are still very important, even when the crack is quite long. Another problem where near tip deformation are dominant in the solution is when we have a system where the forces are a priori unknown, and they have to be defined through the imposition of kinematic condition. This is the case, for instance, of the novel inverted 4-point bending test, which you can see there on top. And in this specimen, there is contact between the layers near the midspan. And in order to define the contact forces, we have to apply some compatibility condition in the displacement of the layer. And this compatibility condition must account for the near tip deformation to obtain a correct solution of the problem. And finally, the near tip deformation are very important when dealing with coating or thin films on substrate. For instance, when we consider the problem of buckle-driven delamination, because the buckling load obviously is strongly affected by imperfect clamping conditions. So in our work, we have considered a bimaterial isotropic or orthotropic layer subjected to arbitrary end loadings. And we describe the end loadings by moving to the crack tip and considering 6 elementary loading modes: pure bending, axial forces, double shear, single shear, and the void loading. Void loading are those modes that do not create singularity in the crack tip. And here you see the formulas to obtain this crack tip loading as function of the externally applied loading. And then we consider 6 elementary kinematic variables, which are root rotations and root displacement at the crack tip cross section. And you can see them there in the schematics. So the aim of our work is to define a matrix of compliant coefficients which relate the loading parameters, the loading modes, to the kinematic variables. And in order to obtain this compliant coefficient, we have extended to the elasticity a technique which was originally developed by Martin Andrews and myself using beam theory. So the idea is to define the stress fields far away from the crack tip, an exact solution of the stress field, then to apply there the reciprocity theorem of elasticity, and to apply the J integral using 2 different forms of the J integral. The first is in terms of global forces and moment. The second is in terms of the local stress and strain fields. By doing this, we have a set of relationships that we can now use in order to define the compliance coefficient. And here at the bottom, you see 2 examples of compliance coefficient. They depend on the elastic properties, on the geometry, and on the term of the J integral. So this means that if we have an expression for the energy release rate, and if we have a new result for the energy release rate, they can be exact or numerical, then we are able to define all the compliance coefficients. We have applied this technique to a few problems. I'm just showing you one of our results. So if we consider an orthotropic strip, like the one shown there, then in this case, we are able to define almost all the coefficients of the matrix, but 4. And we can obtain explicit expression for the coefficient. Let me just show you one of them. And the coefficient will depend on the orthotropy ratios, lambda and rho. And by the way, this solution is valid for the whole range of orthotropy ratios, admissible range of orthotropy ratios. And it also depends on those 2 functions, y1 and y2, that we previously defined through an accurate exact elasticity solution of the problem for the energy release rate. So just to conclude, so we have developed a novel elasticity technique to derive elastic clamping boundary conditions for beam plate theories used to describe detaching by layers. By using this technique, we have been able to obtain explicit closed form expression for the problem of bimaterial isotropic layers with equal thickness layer, for symmetric orthotropic layers, and for thin films on thick substrate. The solutions are also for material with extreme elastic mismatch and extreme orthotropy ratio, which is very important because we can use them in the novel materials which are used in nowadays applications. And the solutions are also applicable to general cases by using analytical and numerical solutions for the energy release rate.